In episode 3, I presented a formula that allows for anyone to calculate lengths in Geometry Dash. However, there is a small error that's not caused by the formula. Hello, Count Sacke here, back with another GD Dynamics video. Today we are going to talk about the absolute error found when using the relative scale length formula to calculate lengths. You'll need to watch episodes 1 and 3 for this episode so that things make sense. Lastly, I highly recommend seeing episode 4 to understand some basic statistics. If the terms standard deviation and mean sound unfamiliar, you really should watch it. With that, let's get started. First off, here is the relative length formula where m is a measured length in pixels and beta is the amount of pixels per block. This formula allows you to measure any length in GD. However, there is a problem. It doesn't always give the exact correct value, and it's not the formula's fault. It's our computer screen's display's fault. Now, before you go buy another monitor, there's nothing wrong with your display. You won't actually notice anything wrong, but if you're trying to get very accurate measurements of length, then there is a problem. The issue lies in the way that things are rendered on displays. A pixel is the smallest unit area that a computer can display, but if there's something that takes up a fraction of the pixel, it is unable to be displayed accurately. It either completely fills up the area or leaves it empty. This is a pretty big issue when your only way of measuring lengths in GD is through pixel measurements. Because of this consequence, it now makes us question the accuracy of the formula. Particularly, here are two questions one might ask. How does the relative length formula calculation deviate from the true length for each of the scales? And is there a significant difference in the actual length and the calculated length from the formula? To actually answer these questions, we need to do research. Let me introduce to you the null and alternative hypothesis. The null hypothesis, H0, is basically the expected outcome, common consensus, or population mean. The alternative hypothesis is the statement that opposes the null hypothesis. To actually come up with a hypothesis, you need variables. In any research, you have the dependent, independent, and control variables. The dependent variable is a factor that relies on the independent variable and ultimately undergoes some sort of change. The independent variable is a factor that doesn't rely on others and affects the dependent variable in some way. Finally, the control variable is just a factor that is constant and doesn't change. In the current situation, these are the variables I came up with. The independent variable is the calculated length, the dependent variable is the relative error, and lastly, the control variable is the true length. The calculated length is simply the output of the relative length formula, so x is equal to m divided by beta. The true value is the actual length of the line as a set integer amount of blocks long. This means that we already know the exact value of the actual length because it is predetermined when the line is made. The relative error is a factor that shows how much the calculated value differs from the true value. First off, we have the absolute error. We're using absolute error instead of deviation because we are only concerned by how much the calculated values deviates from the true values. When calculating the deviation mean, it would tend to go towards 0 because the deviation includes both positive and negative numbers. In a sense, you get a balance, but this is a rather misleading idea, so we're only focusing on the overall difference. So the relative error is just the absolute error divided by the true value, so epsilon r is equal to epsilon divided by chi. Now that we have our variables, we can now make our null hypothesis. The calculated length from the relative length formula does not deviate by more than 1% from its true length. This is my null hypothesis because the formula is supposed to be very accurate, so it's like a common consensus in a sense. And a 1% error should be good enough. The alternative hypothesis should be very easy to write now. The calculated length from the relative length formula deviates by more than 1% from its true length. Let's get into the methodology. In the GD level editor, place down the default block. Next, place a line with a set integer amount of blocks long. Zoom in the closest you possibly can and take a screenshot. In that screenshot, measure the length of the default block along the same axis the line is along. Next, measure the length of the line. Finally, calculate the values for x and epsilon r. After that, zoom out once and repeat from taking the screenshot until you zoomed out the most you can. Once you've zoomed out the most you can, you have one sample of data. Then you can make the line longer and repeat all of the steps. I really only got 7 samples. If that sounds lazy, let me break this down for you. There are a total of 20 different scales that you can view in the level editor. The smallest line that you can place with an integer length value is obviously 1 block, and the largest I had was 7 blocks long. So I had a total of 140 different calculations just to answer the first question. So yeah, let's get into the data. Keep in mind that my screen resolution is 1920 by 1080 pixels, and this might affect some results if you were to decide to do this experiment on your own with a different resolution. Here is the data and in the table. To interpret the data, we'll have to consider that there are multiple scales. The reason why is because different scales obviously have different accuracies. This means we'll have to calculate the accuracy of the formula for each of the 20 different scales. I would like to define the closest you can zoom in as scale 1 and the farthest you can zoom out as scale 19 to make things easier. So here is the relative error for each scale. Looking at the data, we can see that for scales 1 to 16, we fail to reject the null hypothesis because the relative errors are all less than or equal to 0.01. However, for scales 17 to 19, we can clearly see that we can reject the null hypothesis because the relative errors of such are greater than 0.01. So now let's answer the second question. How do we quantitatively determine significance? Well, again, statistics as you covered. Welcome to the world of hypothesis testing and the statistical treatment called the t-test. This is a statistical test that determines whether or not there is any significant difference between two sets of data. The t-test actually has multiple outputs, however the calculations for these are things you'd never want to do by hand, like ever. So instead, we get a computer program to do the math for us. However, statistics outputs numbers, not yes or no. So it's really up to a person to be able to draw conclusions. Well, viewer, you're lucky to have someone who had a basic stats class who can interpret this. First is the t-statistic or t-stat. This tells you how many sample distribution standard deviations away a sample mean is from a population mean. A t-stat a lot further than 0 or a larger value says that the means are more different than each other. But a t-stat smaller or closer to 0 says the means are similar to each other. Second is the p-value. This is the probability of getting data at least as extreme as your data, assuming that the null hypothesis is true. There are actually 2 types of p-values, one-tailed and two-tailed, but I would need to talk about the geometric interpretations, which I'll do later. Third is the level of significance, alpha. This value is a percentage or a value from 0 to 1. You take alpha and compare it with the p-value. If the p-value is less than alpha, then you reject the null hypothesis. If the p-value is greater than or equal to alpha, you fail to reject the null hypothesis. Alpha can actually be set to whatever you want. This is because whether or not the data shows any significance to you is still subjective. An alpha closer to 1 states you believe H0 is likely true, but if it's closer to 0, you believe in the alternative hypothesis. Often, alpha is 0.5, but it really just depends on you and the scenario. Lastly is the t-critical value. This tells us how many sample standard deviations alpha is from the mean. Based solely on its name, you should be able to tell that this value is a tipping point in regards to statistical significance. If the t-stat is greater than the t-critical value, this means you would reject the null hypothesis. And if the t-stat is less than or equal to the t-critical value, you fail to reject the null hypothesis. Once again, there are actually two types, one and two-tailed. If you were like me, you would be wondering why does a larger p-value support the null hypothesis? Because by definition, it states there's a higher probability of more extreme values. Sounds very contradicting if you ask me. However, throw away that definition and completely disregard it. We need to talk about a normal distribution. This bell curve shape is a normal distribution. At the center, the value is related to whatever the null hypothesis is. But for the case of the t-test, it's simply the population mean. For the t-stat, you would need to have a calculated sample mean, and this distance between the middle and the sample mean is the t-stat. The area under this curve from the left or right tail end to the t-stat point is the p-value. This is an example of a one-tailed p-value, but if you do this on both sides, where the area comes from both ends, then it's two-tailed. But where is alpha and the t-critical value? Well, it turns out the total area under any normal distribution is exactly 1, or 100%. Alpha is the percentage under the curve from the tail end, and the t-critical value is the distance from the center point where alpha reaches, as shown here. This is cool, but it doesn't answer our question from earlier. I mentioned a normal distribution, but it really helps to understand where the bell curve shape comes from. Let's say we have a bunch of data. Most of the values would tend to close in on a specific value. This is the population mean, and that's the center of the normal distribution. However, keep in mind, there still could be outliers which actually represent the tail ends or the shorter sides of the normal distribution. As stated earlier, h0 is the commonly accepted value, or the population mean, which is the center of the normal distribution. If your data sample mean is similar to the null hypothesis, it would have to be closer to the center of the normal distribution. And the closer you are to the center, the larger the p-value and the smaller the t-stat is. However, if the sample mean is very different from the null hypothesis, it would have to appear on the tail ends and the area under the curve would be smaller. This is why a large p-value with a small t-stat supports and a small p-value with a large t-stat opposes. Let's now put everything together. Based on the definitions of the t-critical value and the level of significance, these two are different interpretations of the same concept. They distinguish or define a point at which a sample becomes significantly different or similar to the population. Now the t-stat and p-value, again, are different representations of the same concept. They tell us how similar a sample is to the population. For a visual representation, let's say we have set the level of significance and t-critical to this. If the sample is statistically insignificant from the null hypothesis, we can easily see that our p-value is greater than alpha and the t-stat is less than the t-critical. Therefore, we would fail to reject h0. If the sample is statistically significant from the null hypothesis, again, we can see that the p-value is less than alpha and the t-stat is greater than the t-critical. Therefore, we would reject the null hypothesis. Alright, I understand that this can be pretty difficult to understand. If you're still confused, here's a summary. The t-stat and the p-value tell us how similar the data is. The t-critical and level of significance alpha tell us what difference in the data is statistically significant or not. If the p-value is less than alpha and the t-stat is greater than the t-critical, then you reject the null hypothesis. If the p-value is greater than or equal to alpha and the t-stat is less than or equal to the t-critical value, you fail to reject the null hypothesis. In our case, we would need to consider two-tailed values since the calculated length can be larger or smaller than the true length. I'll also be using an alpha of 0.99 because I'm very confident in the null hypothesis. So let's see the results of the t-test and I'll be here to interpret it for you. These are the t-stat values and these are the two-tailed p-values. For scales 1 to 18, we see that the p-values are greater than or equal to alpha, and the t-stat is less than or equal to the t-critical value. So we fail to reject the null hypothesis. Therefore, the difference between the true value and the calculated value is insignificant. However, for scale 19, the difference is significant. This makes sense because the further away you are from something, details become difficult to make out. While the terms insignificant may sound easy for us to understand, that won't always be the case. So we actually need to explain what it means in terms of our experiment. In conclusion, the t-test results show that the length formula is accurate to within a 1% error margin for scales 1 to 18, but on 19, the length formula is inaccurate. I would like to mention some things before ending off. When looking at the screenshots, the scale for each axis would be preserved across the entire image. Consequently, that means if the true value and calculated values are equal, that means all integer lengths in the image along that axis are 100% accurate in the relative scale formula. Now, I didn't actually use those in my data, however, it's just something I noticed. And, well, think about it. Despite all the errors that I've calculated and analyzed, the way that the pixels are rendered behave in a predictable way. Unfortunately, there still is no 100% guarantee for non-integer lengths. Remember what I said at the start of the episode? A pixel is the smallest unit area that a computer can display, but if there's something that takes up a fraction of the pixel, it is unable to be displayed accurately. It either completely fills up the area or leaves it empty. This is a pretty big issue when your only way of measuring lengths in GD is through pixel measurements. I hope that you guys can trust the length formula because there actually isn't a more accurate formula. The length formula actually doesn't just apply to GD, it applies to anything that has some sort of scale. The reason why is because it uses basic concepts about ratios, where if we know that y divided by x is equal to a constant, then y is equal to that constant times x, which is just simple algebra. Now, the formula isn't actually complete, but keep in mind that my methods used in this video are in places where the formula is intended to be used. If you're wondering the cases where the relative length formula cannot be used, you'll have to wait for another episode because that would require 20 to 30 minutes worth of content on its own. I do plan on making a dedicated video about the different ways length measurements can be done in GD. However, this one might have to wait a while because I would need to discuss the quote-unquote complete length formula and another one at that to be able to even know these methods are possible. Well, at the end of the day, we can only hope the pixels don't lie. Let's end things off. I wrote this episode as if it were an informal research paper. If you are someone who loves science and/or mathematics, then get used to doing quantitative research. Doing this study, albeit about a formula used for a video game, really did refresh me on how to properly apply statistics to data. And, well, yeah. That's really about it for now, so thanks for watching and hope you've enjoyed.